As I mentioned in the previous video, we actually have different models of light. So this is what, when we say models of light, we're talking about like kind of the characteristics of light and how it interacts with its surroundings. And there's two major models of light that have come up through the study of physics and light, and we're going to discuss both of them. So historically, we had this thing called the particle model of light, sometimes referred to as the corpuscular theory. And this was a very prominent way back in the days of Sir Isaac Newton. He also was a person who did a lot of developments in the particle model. So not only did he develop parts of it, he also supported it. And Sir Isaac Newton, being kind of like the heavyweight in physics that he is, if he said, well, I support the particle model of light, you weren't prepared to question that. Like, not Einstein, Newton was pretty much like the king of physics. So if he said something, you were going to believe that. So when we talk about a particle, we're talking about a discrete unit of matter. We're going to say it has mass, it has momentum, has the ability to carry electric charge. We're not too worried about that part. Now, of course, if we have a model, usually we get models from evidence or from our observations. So there were certain observations that lend credence to this particle model of light. So first of all, EMR propagates in straight lines. Sometimes this is referred to as rectilinear propagation. That was evidence for the particle model. Particles, like for example, if you take a ball and throw it against a wall, it's going to reflect off the wall. Well, electromagnetic radiation is known to reflect. That was also evidence that it was behaving like a particle. And electromagnetic radiation could also be absorbed by surfaces. So for example, if you throw a ball in the water, the ball is going to get, we'll say, absorbed by the water. This is also evidence that it's treated like a particle. Now, Newton also gave an analogy with light. So you have to think, for example, if you're like tossing, again, we're going back to the ball. If you toss a ball real slow, it's going to be really obvious that the force of gravity is acting on it. So like, for example, if I toss a ball and I toss it really slow, you're going to notice that it comes back down to the ground really quickly because of the force of gravity. But if I take that ball and I throw it the same distance, but I throw it significantly faster, you're probably going to not notice much of a drop here. And what Newton had theorized is, well, if light travels in a straight line and we notice that it's not dropping any, or we don't notice this drop, what he had hypothesized is, well, for that to occur, light has to be traveling really, really, really fast. So based on the particle model of light, Newton figured light had to be really fast. He didn't have a value for it, and those values came about later, but he was at least on the right track. He knew that it went really fast. Now, I mentioned there was also this thing called the wave model of light. It didn't really gain a lot of traction during Newton's lifetime, again, partly because of Newton. Newton was such a staunch supporter of the particle model, so again, if he said the particle model's right, most people weren't in the position to question that one. Once Newton died, though, the wave model started to get a little bit of steam. It had its origins from a Dutchman named Christian Huygens. So he argued that light, it consisted of waves, and that these waves were made up of even smaller waves called wavelets, which is part of what's known as Huygens' principle. We'll talk about that a little bit more later. So, as we mentioned with models, to get a model, we usually have evidence that supports that model. Well, we had the same thing with the particle model. There was evidence that supported that. So electromagnetic radiation could undergo this principle called diffraction, which we'll talk about later. It could also undergo polarization. We'll also talk about that later. And we could also observe interference. So in Physics 20, when we talked about things like constructive versus destructive interference, we could also observe that with electromagnetic waves. And these properties, as you'll see later, diffraction and polarization, and as you've already seen in Physics 20, interference, these can only be explained if we treat light as a wave. So this gave support to the wave model of light. Now, Huygens, he hypothesized this, but he didn't really have a lot of experimental, really concrete evidence. So we had to wait a little bit for that. And eventually what came along in terms of evidence was this thing called the Young's double slit experiment. And this was done by Thomas Young in 1801. So what he had done, and we're going to talk about Young's double slit in much more detail later, What he had done is he had took a beam of monochromatic light and he had split it into two beams. Now, according to the particle theory, what we would expect is when these two beams come out of these slits, we could expect them to shine on this wall here. Where the beams are overlapping with one another, we'd expect it to be a little bit brighter there. That's what we'd expect with Newton's theory. What was actually observed, though, is we still had these two beams of light, but instead of noticing this nice continuous beam with kind of a brighter patch in the center, we notice this alternating pattern of bright and dark spots. So this is what we call an interference pattern. And these are alternating regions of constructive and destructive interference. Where we have the bright spots, those are regions of constructive interference. Where we have the dark spots, those are regions of destructive interference. The whole concept of an interference pattern can only be explained if we treat light as a wave. So what that means is we now have some nice solid evidence for light behaving as a wave. So we're going to have that tension and that conflict between the particle model and the wave model. But we're going to speak more about that later. And of course, by the time we got to the end of the 19th century, around the 1900s, we had good evidence for the particle model. We had good evidence for the wave model. So the question always came up is, well, which one's correct? We're going to give you an answer to that question later. It might not be the most satisfying answer, but it is the correct answer. And of course, this wasn't all there was to the story. When we got to 1900, we had a very famous German physicist named Max Planck. He proposed that radiation that's emitted from this thing called a black body, he proposed that it could only be emitted in what we call these discrete packets, or we could call this discrete packets quanta. Now, because we could only emit energy in small little bundles, we would say that the energy is quantized, but we're getting ahead of ourselves, and we'll talk about that later. And then what Einstein had done is he said, well, not only can energy be quantized or broken up into these small packets, light itself can also be quantized into these particles that we now know as photons. So Planck and Einstein, they proposed this idea of what's called the quantum model of light. And these packets, or these photons, they displayed both characteristics of particle and wave. So we really threw a lot into the mix here. Now, if you're kind of thinking about this and you're starting to think, what the hell did you just talk about? Or if you're really confused, not a problem with that. This is the joy of quantum mechanics. If you're not confused by it, as Niels Bohr said, you're not doing it right. So this is meant to be confusing, because what we're going to take is we're going to take a lot of the physics that you have learned up to this point, and we're going to turn it upside on his head. Now, I want to give you a nice little analogy to kind of explain this whole particle versus wave model. So in the classroom, to you, you're going to address me as Mr. O'Donnell. I'm your physics teacher. We have that student-teacher relationship, and we have that very formal relationship. So it's not very casual. That's why you're going to address me as Mr. O'Donnell. Now, if I go out and chat with my friends and my family, they're not going to call me Mr. O'Donnell. That's a little awkward socially and other means. They're going to address me by my first name. They're going to address me as Scott because we have that level of familiarity and comfort. Now, I go by Mr. O'Donnell in the classroom. I go by Scott outside of the classroom. But that doesn't mean I'm one or the other. I'm not either Mr. O'Donnell and I'm not just Scott. I am both of those personalities together as one. Which personality you're going to see, the Mr. O'Donnell versus Scott, it's going to depend on the observer who's interacting with me, whether that happens to be students in the classroom or family and friends. This is going to be kind of the same thing with light. Whether we're going to talk about light as a particle or light as a wave is going to depend entirely how we interact with it. The rule of thumb that we have, and it's not a hard fast rule, but generally what we're going to be doing in the course, if the frequency of your EMR is less than that of visible light, we're going to treat it like a wave. If it happens to have frequency that's greater than visible light, then we're going to treat it like a particle. And then visible light itself, that's going to get to play the best of both worlds. We're going to treat it like a wave, or we're going to treat it like a particle. Depends what's going on. So what we're about to explore eventually is we're going to start to explore kind of the surface of the wacky world of quantum mechanics. You're going to have some questions answered, but you're going to have so many questions coming from that are not going to be easy to answer at the high school level. but we are about to introduce you to the joy of modern physics, but we'll get to that a little bit later.